Hello, everyone. Thanks for coming. I am Giuseppe. This is Yulia. We work on the Garden team, and we're going to be talking about what's new in Garden land, what we've been doing in the last few months. First of all, let's go through what Garden is. So Garden is the containers engine that powers Cloud Foundry, but also Concourse and Boschlight. So if you're wondering what a container is, then let's look at that. So containers are effectively just a way to distribute applications. The reason we like them so much is that they offer us encapsulation of all our dependencies and also isolation from any other thing that might be running on the same machine. How do we do this? Well, effectively, containers are, on Linux at least, are nothing more than processes that have been isolated from all the other processes on the system through some primitives that the kernel gives us. And in particular, we're talking about namespaces, which basically allow us to limit what a process can see on the system, and then C groups, which allow us to limit what the process can do on the system. And we've been leveraging these primitives on Cloud Foundry for quite a long time now, since the beginning, actually. We had this containers engine called Warden, which was written in Ruby, actually, and then we rewrote it in Go. We renamed it Garden. And this was all great until in 2013, Docker was released. And it was like this massive revolution. Docker wasn't doing anything special. They were using exactly the same kind of features that we were using. But what they did was they provided this amazing user experience on top of them, which meant like every developer was able to just manage their own containers very, very easily. And they got so popular that basically they became like a de facto standard. Like people started, it was kind of a synonym of containers. When you said Docker, most people meant just containers. And it got so popular that we were like, maybe we should start using this in Cloud Foundry as well. And we tried to integrate it, but the truth is Docker was never a standard. Docker was never conceived to be a reusable piece of software. It was always like this very monolithic system and not very modular. So like in the end, when we tried to integrate this, it didn't really work very well. Luckily, things changed a couple of years later when basically Docker plus another bunch of companies joined forces and they created the Open Container Initiative. And what they did was they basically came up with a really standard format for containers. And they also released a reference implementation for that format, for that specification, which is called runc. And runc is like everything that Docker is not. It's like this very tiny binary, super reusable. It just takes this one spec in, and it runs the container described by the spec. So this was very, very easy for us to integrate, so we did it immediately. And later on, so runc was extracted from Docker. Containerd was released from Docker as well. And the Containerd is this daemon that runs on top of runc and adds a bunch of features on top of it. And once that was released, we also started to integrate with that. So this means that Garden stopped being this like full stack containerization solution. Instead, it became basically just a layer on top of these well-established containerization technologies. And it acts as an abstraction that we're trying to make like as thin as possible, but still very valuable, because basically we are abstracting the rest of the platform from all the changes that are happening in the world of containers. So every time we start supporting a new containerization technology, we are the only ones that have to make changes, basically. The rest of Cloud Foundry can just keep working as usual. And another good thing is that we also have an opportunity at the Garden level to apply our own security standards, our own security defaults. And this is what we do. We basically try to turn on as many security features as we can by default. This is a list of some of the ones that we do turn on by default. And this allows us to get our containers as solid as possible, regardless of what we use to run them. All right, over to you. Let's talk about what we've actually been doing. over the past few months?
So now you know what Garden is, but how did our Garden grow in the last few months? So we spent most of our time working on 3 main tracks, and those are CPU metrics, containerd, and rootless. And I'm going to go through the first one, so CPU metrics. You're probably wondering, Cloud Foundry already has a CPU metric, so when I do CF app, I see some numbers. Why do we need a new one? And you're kind of right, but it has 3 main problems. So the first one, the metric is really confusing. So let's say you push an application to Cloud Foundry and it's using 20% of the CPU. Then you push the exact same instance of the application, doing the exact same amount of work, and all of a sudden you see 200%. So how is that even possible? So the current metric has a few problems, and one of the main problem is that it depends on factors that are not visible by the user. For example, how big the Diego cell is, and are there other applications running on the same Diego cell. So that means that it's super hard for users to understand how much CPU their application actually needs and consumes right now, and when they need to scale. And it also makes auto-scaling just impossible. The other problem is that high CPU applications can currently negatively affect normal applications or low CPU applications. Let's just look at an example. So let's say you have a Diego cell and you have 5 applications running on it, and they're all of the same size. So all of them will get their fair share of 1/5 of the host CPU, or around 1/5 of the host CPU. That doesn't mean that each of the applications won't be allowed to spike over their fair share. They will, if there are some idle resources on the machine, or for example, if the other applications are just using less than their fair CPU. But what will happen if you end up on a Diego cell where all of the applications are consuming as much CPU as they could possibly get? That means that you won't be able to spike even for 1 second over your fair share, which leads to poor user experience, for example, on startup, because a lot of applications just need to temporarily spike on startup. And the third problem is how operators actually solve that problem. So they want to create this perfect world where all of the applications can use their spike CPU. So they just overcommit a lot of CPU that users don't pay for, and it just stays idle for most of the time. So the thing that we want to achieve, we want to make the metric meaningful. So when users see the number, it should actually give them some value. So if the percentage should stay unaffected by outside factors that the user has no way of knowing. And the other thing is the percentage should only change if your instance is actually using more or less CPU. So if the usage changes, it shouldn't be affected by outside factors. The other thing, bad applications should not disadvantage normal apps. And the third thing, we should make life easier for operators. So they should feel comfortable to provision enough CPU on the machine without having to over-provision the amount of CPU so that all of the applications can use their spike CPU all the time. So what did we do? We introduced a thing which is called CPU entitlement. So that is more or less the amount of CPU that your application is allowed to get relative to, so it's being controlled by the instance size. So it's currently relative to the memory. So for example, a 2 GB application will currently get twice as much CPU time as a 1 GB application. And there is also a mapping from memory to CPU that's currently being controlled through a Bosch property. We try to write a document which describes that in details so that operators can easily find the right value for them, depending on the fact if they want to under or over provision CPU. And we also set a default to that value, which just creates a system where all of the applications are guaranteed to always get at least their entitlement. So we split the implementation into 3 main milestones. And the first one is the meaningful metric. So we created a new CPU metric, which is relative to the entitlement. So that means that if you see 100%, that means currently you're using all of the CPU that your instance size allows you to use right now. If you see 105, that means, okay, currently there are some spare CPU resources in the machine and you're allowed to use them in this moment, but you're not guaranteed to get them in future. So the reason we didn't change the old metric is because the behavior is really different and we wanted to give users the time to adapt to the new metric. So we just wrote a plugin, which is called the CPU Entitlement plugin, that exports the new metric. So let's just look at an example to see the difference between the old and the new metric. So let's say you have an application that's running on a Diego cell and it's constantly using around 30% of the host CPU. So for the old metric, it doesn't really matter what your fair share is or how much CPU are you kind of allowed to use. It will always show you 30%. For the new metric, it does make a difference. So if you're using 30 and you're entitled to use 30, you'll see 100%. If you're using 30 out of 60, then it will show you 50%, because for us, we think that it's a big difference if you're using all of the resources that you're paying for, or are like the resources just being idle all of the time and you're just paying for nothing. The second milestone was the operators tooling. So we wanted to create some tools that will allow users and operators to track the average CPU usage compared to the entitlement over time. So at this step, nothing will happen and nothing will change regarding how we give CPU time to applications and containers. We will just observe how the system behaves and try to get some feedback from operators if we're actually going to do the right thing. So we created the CPU Entitlement plugin, as I said, and currently it has a few commands. So let's say you have an application which is called I'm Spiky. If you do cf CPU I'm Spiky, you see that you have one instance, and you can see the average and the current usage. So the current usage is, in this second, what amount of CPU you're using relative to your entitlement. And the average one is, so average from the creation of the container, in our case, or in the last period. So if your behavior changes at some point, you'll be able to see that really quickly in the current behavior, and then it will just start accumulating in the average usage. The thing that matters for us and the future throttling, so the third milestone, is the average usage. And so we also have a few more things that we added to the plugin. So if you're near the entitlement, in our case, it's like 95%. That means that if you continue using that much CPU or a bit more, at some point something could happen. For example, you will get throttled. The other thing is when you're over entitlement, because it should be visible to users if they're using more resources than they depend on. And the other thing is the average use. So is my average usage over the entitlement? And this is going to tell you if your average usage was ever over the entitlement. So not right now, but at some point in the past. And there's also one more command, which is over entitled instances, which will, for each organization, it's going to tell you all of the applications that are currently over their entitlement. That's not fully, so it's fully implemented, but we are going to change this because we're trying to gather feedback from operators right now, what will be useful for them as behavior. So if you have any ideas, feel free to share them with us after the slot. So the third milestone is the throttling one. So here things will start to really change on the system. We haven't started implementing this, but we spiked it, and the plan is the following. So we will have two groups of applications, good ones and bad ones. The good ones are the ones that have been below their entitlement over the last period, and the bad ones, the one that just used more resources than they should have been used in the last period, so since creation. All applications are good by default. If your average usage goes over 100%, you're being moved to the bad group. And when it goes back under 100%, you will be a good application again. So the difference between the two groups is if there are some spare resources on the machine, CPU resources, they will be first given to good applications that want to spike over their entitlement. If there are no good applications that actually need those resources, it will be given to bad ones. And if there are a lot of bad applications that just want to spike over their entitlement, they will be allowed to do that, but that won't negatively affect the good ones. So they should be kind of in isolation. And there are two key points here. So the throttling only happens if there are not sufficient resources for everyone. So if there are enough resources, then both good and bad applications will be able to spike over their entitlement and just use everything that's idle on the system. And the other thing, you're always guaranteed to get your entitlement. It doesn't really matter if you're a good or a bad app, your entitlement is guaranteed. And what we expect to happen, we expect that good apps won't see worse performance than previously. They should even start behaving better because bad apps won't affect them, and the so-called bad apps that just use more resources than they should be using should see that clearly. So if they actually depend on the resources that they're using, they should just scale their instance. And the next track that we worked on is containerd. And Giuseppe will tell us about it.
All right. So, I was talking about how we're basically trying to become this like thinner and thinner layer on top of existing standard containerization technology. When it comes to containerd, I think last time we were on this stage, we talked about how we had all the container-related operations implemented. Today, we can announce that we've pretty much done with all the process operations as well. It's not 100% done, but all the process operations used by Cloud Foundry are implemented, are actually going through containerd, which means that nowadays, if you deploy Cloud Foundry with the containerd flag enabled, everything you do in terms of containers and processes will be going through containerd, which is pretty cool. So we're not done yet. As I said, we want to finish the process lifecycle with adding some operations that currently are used by Concourse, for example. And then once that's done, we're going to start exploring the image lifecycle. So at the moment, we have this plugin called ROOTLESS, which we use for our image things. We want to explore how it will look like to delegate those things to containerd as well. Next, rootless mode. So I talked about security earlier. We want to make sure that like our containers are as solid as possible, so we turn on as many security features as possible by default. But still, there is this like elephant in the room with basically the garden process is running as root, which means if anyone by any chance gets control of the garden process, then they will have root privileges on the system, and of course that's not really nice. So we've been putting lots of work into trying to run the garden server as just a normal process belonging to a normal user. This work for our runc backend is pretty much done. There is an experimental flag that people can turn on. There is still a bunch of work to do on the containerd backend. We'll keep you updated. And being able to run as a normal rootless process also means we can run inside our own container. And this is pretty much exactly what we're doing because the new Bosch process manager uses runc to containerize the jobs on your VM. So when running Garden in rootless mode, you'll be running inside a container which is powered by BPM. And of course, at some point, we want to do this for the containerd backend as well. Okay, so this is all we've been doing in the past few months. These are the tracks we are working on right now. I want to spend just the last 30 seconds talking about what we plan to do in the future. So we all know that the future of like container scheduling on Cloud Foundry is called Kubernetes. And we all know that's what we are aiming at. But at the same time, we know there are gaps, right? We know that there are things that Kubernetes still does not provide and that we do need to run a platform, a multi-tenant platform, an enterprise-level platform like Cloud Foundry. And as a team that's been working on running containers in a multi-tenant environment for like so many years, we think we can help like filling those gaps. So we have identified a bunch of things we could help with. For example, a security profile for multi-tenant apps, the CPU entitlements that you guys just talked about, XFS disk quotas, rootless that I've just mentioned, integration with tools like gvisor or Firecracker, which basically make containers actual real sandboxes, and cold starting. So this is still very much up in the air, but we will definitely sit down and start planning this work concretely very soon. So yeah, that's it. This is the attribution for all the amazing artwork you've seen in the presentation. And that's it. Thank you.